In this video, we'll take a look at electric fields. Specifically, we're going to focus on calculating magnitudes for now. In class, we will talk about how to calculate direction, or how to determine direction, and exactly what we mean by the word field. But for now, again, we're going to focus on just the calculation aspect. Assume we have a charge, Q, somewhere, and that's the charge that we're interested in looking at. In order to determine the strength of the electric field surrounding charge Q, we imagine that we put a test charge, call that lowercase q, some distance away. This test charge has a positive charge of 1 electron, 1 electron's worth of charge, and this test charge can be moved around at different distances to determine the electric field surrounding our charge capital Q in order to determine the strength of the field at different distances away from our charge of interest, which is capital Q. So, an electric field is a vector field, so I'll write that as a vector, and it's equal to the force on this little test charge divided by the strength of that test charge. The units for an electric field are newtons per coulomb, which we can see since it's force over charge. And again, the force that we're talking about is the force of the positive test charge which right now we're calling lowercase q, onto the charge in question, which we are calling capital Q. So it is positive, that's important, it's going to come back and play a role in a little bit. So to calculate the magnitude of the electric field due to our charge in question, capital Q, at some distance away, which we're calling R, we are looking at whatever charge that little test charge has times the force between the two charges. So we'll plug in Coulomb's law for the force. Oops, that's supposed to be multiplied. Which is our proportionality constant K, the charge in question, capital Q, times the charge of our test charge, over the distance between them squared. So we can see it doesn't really matter what the charge of our test charge is, they cancel. So I can rewrite this then as our proportionality constant times the charge in question, the one that's causing the electric field, over the distance squared. We can also rewrite this in terms of the permittivity of free space, just like we did with Coulomb's law. And I'll include that here. It's important to note that since we use Coulomb's law, this is how you calculate the electric field for a single point charge. Which we've been calling Q. So what this means is that if you happen to have a rod or a ball, something like that, that's not a point charge. If we have more than one charge involved, then we'll need to go and use our superpositions, just like we did with forces. So we would have to calculate the electric field due to each individual charge and add them together. Again, this is a vector field, so we would have to break things down into components, just like we did in our final example of Coulomb's law. So, in order to go through and determine the strength of an electric field due to multiple point charges, we do need to know the direction, because we have to break things down into vector components. So we'll save an example of that for later. Right now we'll go ahead and do an example of just one charge and one test charge, similar to what I've drawn above. So So let's assume that we're using the same diagram as what I drew above, and let's give some units to this. So in our example, with the diagram that I drew above, we'll give Q, say that's 2 microcoulombs, and the distance between Q and our test charge is, say, 0.2 meters. So what we want to know is what is the magnitude of the electric field at point P. Which is basically where I put our test charge Q. Remember, this test charge is just there to help us kind of get a feel for how strong this field is. Okay, so the force between that test charge and our charge capital Q is again going to be our proportionality constant, our charge capital Q, the charge on our test charge, the distance between it squared. We can plug this into our formula for the electric field. Just as before, the amount or the magnitude of the charge on the test charge cancels. So we end up with this. We'll go ahead and plug in the values so we can determine numerically the strength of this electric field. Plug in the values so we can determine numerically the strength of this electric field. Convert our microcoulombs to just coulombs as we've done in previous examples. We'll notice that our units of length disappear, our units of charge disappear, or one of our units of charge, disappears. We plug this into our calculator. We'll find, once we round to the correct significant figures, that we've got 400,000 newtons per coulomb of electric field at our point P. Again, the direction of the electric field will be discussed in class, and we will need that in order to calculate the electric field due to multiple point charges. So we'll have a little bit more of discussion in class before we go into further examples of the electric field.